Good morning. Welcome back to our physics class. We had already started the topic radioactivity, in which we had seen the different types of radioactivity, the properties of radiations, like the properties of alpha, beta, and gamma, and the different radioactive decay modes had seen. Today we are going to study the theory behind this radioactivity. So our topic is law of radioactive decay. So we know that the unstable nucleus tries to attain stability by disintegration or by decay process. So this disintegration of radioactive nucleus was studied by Rutherford and Soddy in 1902. According to them, radioactive decay is a statistical process. They concluded that in a given sample of radioactive substance, so the sample contains several nuclei, isn't it? Several atoms, and these atoms have nuclei. So there are more number of nuclei inside a sample. And they said that the various identical nuclei take different times to decay. And we cannot predict the moment of decay or the time of decay of any given nucleus in the sample. The radioactive decay law states that the number of nuclei that will decay per second is directly proportional to the number of atoms present that have not yet decayed. So, if a radioactive sample contains capital N nuclei at a given instant, we can find the rate of decay, that is, the number of nuclei is decreasing with the time. So, if N represents the nuclei in a radioactive sample at a given instant, dN by dt gives you the rate of decay. So, this dN by dt is directly proportional to the number of nuclei present at that instant. So we can write dN by dt is directly proportional to N. So changing the proportionality, we have to add a constant. So dN by dt is equal to minus lambda into N, where lambda is a constant known as the decay constant, or it is also known as disintegration constant. Its value is a characteristic of a radioactive substance, and it gives you the decay probability of the sample, or it represents the probability of decay per unit time. So the law of radioactive decay states that the number of nuclei that will decay per second is proportional to the number of atoms or nuclei present. So dN by dt is directly proportional to n, and dN by dt is equal to minus lambda n. What is that negative sign indicates? The negative sign indicates that the number of nuclei is decreasing with time. So we had got an equation that dN by dt is equal to minus lambda n. Now we can simplify this equation by taking n to left hand side and time, that is dt, to right hand side. And we can simplify that equation and can find out a new equation that connects n and n0, given by n is equal to n0 into e raised to minus lambda t, where n0 represents the number of nuclei originally present. That means the number of nuclei at t is equal to 0. Whereas n represents the number of nuclei at a particular time t. So, if the number of nuclei originally present is n0, by simplifying the above equation, that is dN by dt is equal to minus lambda n, we can see that the number of nuclei of the decaying element present at time t is given by n is equal to n0 e raised to minus lambda t. So we have the equation, first equation, that is according to the law of radioactive decay, dN by dt is equal to minus lambda n. Rearranging and integrating, what you will get, 1 by n dN on integration will give you log n, which is equal to minus lambda t plus c, where c is a constant of integration, and you can find out the value of constant of integration by applying initial conditions. So at the initial time, that means at t equal to 0, what is the value of n? We had said that n is n0 at t equal to 0. So you can apply that condition, that is at t is equal to 0, n is equal to n0. So this condition can be applied in the second equation, and you can find out the value of c as log n0. So again you can substitute the value of c in the second equation. So log n is equal to minus lambda t plus log n0. Again taking the log terms to the left hand side, log a minus log b will be log a by b. So log n by n0 is equal to lambda t. Taking the exponential on left side and right side, we will get n by n0 is equal to e raised to minus lambda t, or n is equal to n0 e raised to minus lambda t. What does this mean? N gives you the number of radioactive nuclei at a particular time t, and n0 is the number of radioactive nuclei at a time t is equal to 0. And this n0 is multiplied with an exponential term, that is e raised to minus lambda t. That means the value of n is decreasing exponentially with time. We can plot the value of n with t and can find out the graph also. So this is an important equation, that is n is equal to n0 e raised to minus lambda t, where n is the number of radioactive nuclei at a given time t, n0 is the number of radioactive nuclei at a time t equal to 0, lambda is the decay constant or disintegration constant, and t is the time. Now half-life. What is meant by half-life of a radioactive element? The time taken for half the radioactive atoms in the element to disintegrate. So in this pink color they have shown 8 radioactive atoms. Now after the half time, what happens? Half of the atoms, that means 4 atoms get decayed and only 4 remains. That means it is the time taken by the radiation from the element to drop to half its original level. In terms of radiation, we can also define. So, half-life of a radioactive element is the time interval during which half of the atoms of the given radioactive sample decay. I repeat, half-life is the time interval during which half of the atoms of the given radioactive sample decay, and it is denoted by capital T or capital T half. Let's have a look on the equation of T half. For that, you can write the law of radioactive decay, that is N is equal to N0 into e raised to minus lambda T. Here N is the number of radioactive nuclei at T time. N0 is the number of radioactive nuclei at time 0. So, we had said that half-life is the time taken for the radioactive sample to decay to half of its initial number. So when time t becomes t half, what will be n? N will be half of the initial value, isn't it? So n will be n0 by 2. So again substitute t as t half and n as n0 by 2. So n0 by 2 is equal to n0 into e raised to minus lambda into t half. N0 gets cancelled. You can take logarithm on both sides. So log 2 is 0.6931 and you will get an equation for t half. T half as 0.693 divided by lambda. That means half-life is inversely proportional to the decay constant. And half-life of a radioactive substance is a characteristic property which cannot be changed by any chemical or physical means. For example, half-life of radium is 1620 years, but that of uranium 92-238 is 4.5 into 10 raised to 9 years. So, this half-life of a radioactive substance is a constant and it cannot be changed by any physical or chemical means. This we had already seen. We have the radioactive decay law, that is N is equal to N0 raised to minus lambda T, and putting T is equal to T half, N will become N0 by 2, and on simplifying we got the expression for T half as 0.693 by lambda. So that this equation gives a relationship between half-life T half and the decay rate lambda. On plotting the equation N is equal to N0 into e raised to minus lambda T, we will obtain a graph like this. You know this is an exponentially decreasing graph, isn't it? So we had taken small t along x-axis and N along y-axis. So initially you can see that the value of N is N0. So N0 is the highest amount of nuclei. Now what happens when time reaches T half? When small t becomes T half, N will become N0 by 2. So you can see when T is equal to T half, N becomes N0 by 2. The corresponding Y value will be N0 by 2. So after one half-life, N0 by 2 will decay and N0 by 2 radioactive nuclei will remain. Now what happens after two half-lives? So initially N0 by 2 were there. After the second half-life, it again becomes half. That is N0 by 2. By 2 means it will be N0 by 4 for the second half-life. That means after two half-lives, N0 by 4 radioactive nuclei are left. And so on. Again here you can see, you can check for 3 half-lives. So what happens? N0 by 8. After 4 half-lives, it will be N0 by 16. So in general, the number of nuclei remaining after N half-lives will be N0 by 2 raised to N. See, initially we had N0, then N0 by 2, then N0 by 4, N0 by 8, N0 by 16 and so on. So after N half-lives, it will be N0 by 2 raised to N. The number of nuclei remaining after N half-lives is N0 by 2 raised to N. So that's why we are saying the decay of a radioactive nucleus is a statistical process. If we take a radioactive sample of 1 milligram with a half-life of 1 hour, I repeat, we have a radioactive sample of 1 milligram with a half-life of 1 hour. What happens? After 1 hour, 50% will decay. Isn't it? And what about the second hour? During the second hour, the probability of decay is still 50% for each remaining nucleus. So what will be the total probability that a nucleus did not decay? After 1 hour, 50% got decayed and 50% remains. And after the second hour, again the probability of decay is 50%. So what will be the total probability? 0.5 into 0.5. So that is 0.25. That is the probability that a given nucleus did not decay. If it is the probability for the nucleus not to decay, then what is the probability of decay? It will be 0.75. I repeat, after 1 hour, 50% will decay, and during the second hour, probability of decay is still 50% for each remaining nucleus. So the total probability that a given nucleus did not decay is 0.5 into 0.5, that is 0.25 or 25%. That means the probability of decay is 75%. So from this we can conclude that the decay of radioactive nucleus is a statistical process. This is explained again, the decay curve for a radioactive element. Here you can see that dn by dt is proportional to n and dn by dt is equal to minus lambda, and on simplifying that equation we had obtained n equal to n0 e raised to minus lambda t. And n gets decreased by n0 by 2 after first half-life, then it gets decreased to n0 by 4 after second half-life, then it gets decreased by n0 by 8, then n0 by 16 and n0 by 32. So we have the equation n is equal to n0 e raised to minus lambda t. Just to substitute lambda as 1 by t. But we will get n will be n0 e raised to minus 1. That is n0 by e. Substituting the value of e, we will get 0.368 in n0. In terms of percentage, we can write it as 36.8% n0. And we had substituted lambda as 1 by t. When lambda is 1 by t, we got n is equal to 36.8% of n0. So how we can define decay constant or disintegration constant lambda? It is the inverse of time, that is 1 by t, during which the number of atoms in a radioactive sample is reduced to 36.8% of their original value. So that is a decay constant. Substituting lambda as 1 by t, we got n is equal to 36.8% n0. So we can define decay constant as the inverse of time during which the number of atoms in a radioactive sample is reduced to 36.8% of their original value. So it is a disintegration constant, isn't it? Decay constant is also known as the disintegration constant, which gives you the probability that an individual nuclei will decay within a unit of time. We had the equation dn by dt is equal to lambda n, isn't it? So you can write a lambda as dn by dt divided by n. So lambda will have a unit second inverse. So if lambda is equal to 0.2 second inverse, what does it mean? Every nucleus has a 0.2 chance of decaying in 1 second. So it gives you the probability that an individual nucleus will decay within a unit of time or within a second. So we had said decay constant or disintegration constant, and we know that the disintegration will take place as the time passes. So the number of disintegrations per second of a radioactive sample is called activity, or we can simply define it as the decay rate of the radioactive sample. Decay rate means the rate at which the number of radioactive nuclei decreases with the time. So we can define activity as the decay rate of the radioactive sample or as the number of disintegrations per second of the radioactive sample. So it is given by dn by dt. And this activity is denoted by capital R. So R is equal to dn by dt. And we had already had the equation that dn by dt is equal to minus lambda n, isn't it? So R is equal to lambda n. Here the activity is given capital A, or we can use capital R also, so that A equal to R is equal to dn by dt, which is equal to lambda n. And the SI unit of activity is becquerel, BQ, where 1 decay per second is known as 1 becquerel. So 1 becquerel is 1 decay per second. Traditionally, curie has been used as the unit of activity, in which 1 curie is equal to 3.7 into 10 raised to 10 decays per second. There is also another unit, that is Rutherford. Where 1 Rutherford is equal to 10 raised to 6 disintegrations per second or decay per second. I repeat, 1 Rutherford is equal to 10 raised to 6 disintegrations per second. Let's see how we can calculate the activity of a given sample. Suppose the given sample contains m grams of the radioactive element X. So we have m grams of the radioactive element. Then how we will calculate the number of atoms? Number of atoms is given by the equation capital N is equal to 1 gram contains Avogadro number. So m gram contains m into Na by A, where A is the mass number. So N is given by m into Na by A, where Na is the Avogadro number. So you can calculate R or activity as lambda into N. So lambda multiplied with m into Na by A. Now lambda can be replaced with the help of the equation 0.693 by T half. So here also you can calculate R as 0.693 by T half m into Na by A. So already we have the equation for activity as R is equal to dN by dt is equal to lambda N. If we are given the grams of radioactive element, we can use this equation to get the value of activity. We had already seen the law of radioactive decay in terms of number of radioactive nuclei. But here we can rewrite the equation in terms of activity also. So we can write R of t as R0 into e raised to minus lambda t, where R of t is the decay rate at time t, R0 is the initial decay rate, and lambda is the decay constant. So R of t is gives you the rate of decay, that is activity at a particular time t, and R0 is the initial activity. We had already seen the SI units of activity, that is becquerel. 1 becquerel is equal to 1 decay per second, 1 curie is equal to 3.7 into 10 raised to 10 decays per second, and Rutherford, 1 Rutherford is equal to 10 raised to 6 disintegrations per second. SI unit of activity is becquerel. Now the last topic is mean life. What is mean lifetime? Represented by tau. Mean lifetime is defined as the average time the nucleus survives before it decays. It is the average time the nucleus survives before it decays. So how we can calculate this mean life? It is an average life, isn't it? So it can be determined by calculating the total lifetime of all the nucleus initially present. Total lifetime, we take the total lifetime of all the nuclei initially present and dividing it with the total number of nuclei. I repeat, mean lifetime or average lifetime of a radioactive sample is defined as the average time the nucleus survives before it decays, which can be calculated by calculating the total time of all the nuclei initially present, dividing by it by the total number of nuclei. So if capital N is the number of atoms present at any instant t, and in time dt, dn of them get disintegrated, tau is given by integral 0 to infinity dn by n0. We have the value n is equal to n0 into e raised to minus lambda t. So we can find out what is dn. By integrating that equation, we will get dn as n0 lambda into e raised to minus lambda t dt. And divide it with the new n0. Then integrate it. Give the limits from 0 to infinity. We know that the integral variable is dn. So for dn, the initial value is n0 and the final value is n. So n0 to n. See, we had write tau as dn is the number of nuclei disintegrated in a time dt. So the total time is into t. So t into dn is the numerator, dividing with the total number of nuclei. That is n0 is the total number of initial nuclei, isn't it? So t into dn gives you the total time divided by total number is n0. Here the integration is dn with respect to n, that is the differential term is dn. So the integration limits must be from initial value of n is n0 and the final value is n. So you have to write integral n0 to n t dn divided by n0. Now we have n is equal to n0 into e raised to minus lambda t. Now you can replace dn with n0 lambda into e raised to minus lambda t. So now the differential changed to dt. So from dn to dt. That means integral limits has to be changed from n to time. So initially the time was 0 and finally the time was infinity. So 0 to infinity integral t n0 minus lambda e raised to minus lambda t dt divided by n0. It's easy to simplify the integration, give the limits, upper limit and lower limit, and you can find out the value of mean life or average lifetime as 1 by lambda. That means average life is the reciprocal of the disintegration constant or decay constant. Or we know that lambda is equal to 0.693 by t half. So you can substitute the value of lambda here and can find out the value of tau as t half by 0.693. I hope today's class is clear to you. We had seen the law of radioactive decay, from where we derived the equation n equal to n0 into e raised to minus lambda t. We had seen what is a half-life and expression for half-life of a radioactive substance, and also we had seen the graph connecting n and t, radioactivity of a given sample, that is activity given by R or capital A, its units, how we had defined the decay constant as 1 by T, and the last topic is mean life, which is given by as the reciprocal of disintegration constant. I hope the class is clear to you. For any doubts, feel free to contact. Thank you.